Okay.
Or Miss Glazer. Well, she's got her doctorate yet. I know she's doing her dissertation now. So we are coming up on test 5. Okay, so just to kind of give you a heads up for section-wise, so you all have, can you all see that calendar down there in the kind of corner right here? So this is the last day of class, but we do not meet that day, from what I've been told. Is that correct? You do not have class on that 25th, so you will not have an SI session then. And then we don't come back until this Monday, the 30th. You have a test that day. We come back, okay? That's your test 5 on the 30th there. So what we're going to do is that weekend, that Thursday, Friday, Saturday, Sunday, I tried putting the link up and it's still not working, so I'm going to try it one more time. If not, I'm going to have Dr. Burns do an internal link for survey, and then you all will vote on what day and time is the most popular. It's probably going to be like a midday time, and we'll do a 3-hour block where probably the first half will be studied for the test and the second half will be studied for final. So just kind of doing some review, because this week here comes up on finals week. Okay, so the week of the 7th is finals. So once we come back that week, you've got one more week, and we'll do review that week in here, and then we've got our final on the, let's see, for you all, because you all are 2 to 3, Monday, Wednesday.
So our final will be on Monday, 7th.
That's what I'm looking right now.
Wednesday.
You're talking about final?
Yeah.
I think it's
So,
7 or...
about December 6th or something?
It's either going to be the
7th?
it's either going to be the 7th or the 9th.
7th.
Yeah, I think you're going to be on the
Monday.
7th. Yep. So it falls in that time on the 7th, and you're going to fall in the.
It's for 2 hours, right?
You have an hour and 20 minutes. So you have basically 2 class periods. So the test is from 2:30 to 4:20. So you have just inside of 2 hours.
So how many questions?
50 multiple choice.
Wow.
So,
But the way you need to kind of think of it is it's 10 questions from each test. You had 5 tests, broke up throughout the semester. Now, the breakup of it is kind of varying. It's more weighted towards the second half. So you're going to have more questions from tests 3, 4, and 5 than you are from tests 1 and 2. Okay? But 50 multiple choice questions. I just want to kind of give you all a heads up on that. So look on course content. I want to get it done by today, so after class, be looking for that up there. Okay, so what questions do y'all have? About the packet? Anything? Have y'all gotten to equivalence yet?
No,
No? Okay.
that's today.
That's today. I expect y'all to come to the study session with questions Monday, because that will be your last one, unless you're going to be able to come to that 3-hour. That's going to be your last one to ask questions. Equivalence is the primary portion of this test. We can't stress enough that this test is 90 to 95% calculation. The only conceptual material on there is definitions. That's it. There's going to be no everything else is going to be plug and chug math. So for the people who are really good with algebra and calculations and stuff like this, you all have to knock this test out of the water. I'll be your best one. But people who are really good with conceptual, they may struggle a little bit with this test. We've done a lot of the gas law stuff. I'm going to do some of these combined gas law problems. If no one has any other questions, does anyone have any other questions? Or want to work any other problems?
Just going over everything we did.
Okay. So, combined gas law, unlike ideal gas law, has some really cool comparisons we can make. So, if you kind of look at this equation here and you kind of compare it to something we know or we've seen before, it kind of looks like our dilution equation, right? It has the very same kind of setup and very same kind of look and feel to that. And that's, in a way, kind of what you're doing. You're either shrinking or expanding the volume, or you're shrinking and expanding, heating up or cooling the temperature, or increasing or decreasing the pressure. So you've got either an increase or a decrease happening here, okay? And what's really cool about your combined gas law is there's three things for it that you don't have to change the units of. So whenever you're using your combined gas law, you do not have to change the units for pressure, or for moles, or for volume. Whatever they are when they're given to you, you can use them just like they are, okay? Because you have no R, okay? The only reason in the ideal gas law that we have to change all the units to moles, liters, and Kelvin, and ATM is because we have that R gas constant. Because this doesn't, we don't have to change these three units. But there is one unit you still have to change because otherwise it'll be negative, and that's temperature. You always, no matter whether it's the ideal or the combined, you have to change temperature to Kelvin. You have to get it in the absolute scale so you don't have negatives. Because you can have a negative Fahrenheit and you can have a negative Celsius, but you can't have a negative Kelvin. Okay? So let's set up this problem here for number 6. So we're told, oh, I don't have y'all sign in. What about that? So let's set up this problem here. So we're going to set up P1, V1, N1, T1 is equal to P2, V2, N2, T2. And you always want to set it up like this and then eliminate the things that you don't have. So it's not as important on this problem, but you kind of want to know what your gas is. So if you're told methane gas, you want to underline or kind of circle that and remember that. So we're told a pressure here and a temp here. And then we're told a second temperature. And we're looking for a second pressure. Anywhere in there, does anyone see anything about the volume of this gas or the moles of this gas or anything like that? No. So you want to eliminate out your volumes and moles. All we really care about is the comparison between pressure and temperature and pressure and temperature. So the pressure that it starts out at here is 30,000 torr. Again, with pressure, I didn't have to change the units, but with temperature we do. Okay, so for this first temperature, it's going to be 273.15 plus that. So you should get 298 Kelvin. Okay, we're looking for our second pressure. So we're looking for our P2. We have our T2. This still needs to be converted. So that'd be 373 Kelvin. So divide these together, multiply them by 373, solving for P2. You should get, it'll be like 3758 or 3757 or something like that. Let's see exactly what it comes out to be.
I got 37550.
Okay.
And then 3 sig figs.
3 sig figs, so that's why we're rounding up to this 376 here. You could also put this in ATM. This answer is perfectly okay. Torr is perfectly okay because we didn't have to convert this. In the problem, he said, what will the pressure be at 100 degrees C? Now, he could ask for one unit or the other by saying, what will the pressure be in ATMs at 100 degrees C? Or what will the pressure be in torr at that? And then he's asking for one or the other. Normally, when you have a pressure that's this huge, you want to get it in something kind of more understandable. It's hard to think about this 37,600 torr, thinking your conversion factor is 760, right? But we know atmospheric pressure is 1. So we can kind of think of this, we can look at it immediately and go, oh, this is 49 times higher than atmospheric pressure. You can't immediately look at that and say, okay, this is, that much larger. Okay?
So why don't we have to count B and N?
Okay, so as long as they're not influencing the problem, what we're being told is that somehow they used a vessel that was not expanding or changing. So the only way the volume could, so they increased the pressure. We saw the pressure went from 30,000 torr to 37,600 torr. So there must have been a strong enough container to keep that gas from expanding, because otherwise the volume would have changed. So what happened is the volume, say it was, they didn't tell us this, but say it started at 10 liters, it never expanded anymore or contracted. It stayed exactly 10 liters. And they didn't add or take away any gas, so your moles of gas didn't change. Okay, so number 7. So we're told we have a sample of gases. So we have a sample of a bunch of different stuff in there. This time we have a volume, right? We have a volume. We have a pressure. And then we're asked what will the pressure become if the gas is compressed down to 1.25 liters. Okay, so writing up your ideal gas law, your combined gas law. Okay. We do not have a moles, and there's no temperature mentioned anywhere in there. Okay. So even though we compressed the gas, the amount of gas didn't change, and the temperature of the gas didn't change. So our first pressure is 2,000 torr. And your first volume is 5.50 liters. And we're looking, we're looking for your second pressure. And we're told the second volume is 1.25 liters. Okay, so just multiply these two together. Divide by 1.25 liters, you're going to solve in torr. Again, torr is acceptable because we don't have to convert the units for combined. You don't have to convert pressure, moles, or volume, because you can't have a negative pressure. So you can't have a negative pressure on something. You can't have a negative quantity of moles, and you can't have a negative volume. But you can't have negative temperature if you don't convert to Kelvin. So always have to convert temperature. So a lot of these are going to be like this right on the test. You got to be able to know your equation, set it up, and calculate. There's not a lot of conceptual to this. Is there any questions? Yeah.
Yeah, it's not about that, but when we get the chance, could we go over question 30 and 31?
30, 31?
Yeah.
Mm-hmm. Yeah, if y'all have any questions, stop me anywhere. I was just kind of going down through here. Question 30, I think that's into equivalence.
Yeah,
Y'all
I
have
actually haven't started it yet, but I'm like doing the 50 quizzes and I'm like apparently on that.
Okay. So for him, if y'all want to listen to this, that's fine. If not, just kind of zone it out. No, we're going to cover it today. So we're told we have a solution that contains a unknown vanadium nitrate compound. Okay. So we know it's got some vanadium. We know it's got some nitrate. We're told 2 grams of potassium are added, and we're told that we have 0.521 grams of vanadium are removed. And we're asked to determine the charge on vanadium in a solution and then write the balanced chemical equation for the reaction. Okay, so the first thing you want to do is we're going to have our 2 grams of potassium. I'm trying to think of the best way to do this, because these want the charge of the vanadium. So you're going to use equivalents per mole on this. Okay. So we're going to get to moles first for potassium here. So the molar mass for potassium is 39.0983. And then we want what's called the equivalence per mole of potassium. The equivalence per mole of potassium is just a fancy way of saying absolute value of charge. So what is the charge for potassium? Plus 1. So we need to cancel units, so we need to have moles on bottom. So for every 1 mole of potassium, you have 1 equivalence of potassium, okay?
So equivalent is just the charge?
I'm sorry?
Equivalent is just the charge?
Equivalent is the absolute value of the charge. You have to use absolute value because for something like oxygen, where the charge is -2, you need absolute value to get 2. So oxygen will have 2 equivalents because of its charge. Okay, and this is going to give us equivalence of potassium. So somebody do this first calculation part here, because then we need to take that to another step. Okay, and that's going to be equivalence here. And when we talk about equivalence, equivalence is really important because, like in a case like this, where we don't have a charge and we don't have a balanced chemical equation, you'd think that we can't do anything. But equivalences are equal when they react with one another. So if I start off with this much equivalence of potassium, it's going to react with exactly that much equivalence of your vanadium. Okay, so now you have your equivalence of potassium, but that means you said, okay, so what happens is it reacts with exactly this many equivalents of vanadium. Okay, and we can kind of start working back towards vanadium now. So now we need to undo the part for vanadium, but we only have the equivalents. But we know the equivalent weight is what? You've been working on this, so you're the only person that can answer the question.
Would it be 1?
Well, we don't know, right? We don't know the equivalent weight for vanadium because we're asked to find the charge. So not looking at that and cheating, your equivalence is equal to your molar mass divided by the absolute value of your charge. So now we have the equivalence. We can get its molar mass, and what we're really wanting to solve for is the whole thing we've done all this for is the charge. So we're just going to plug everything in here. So we have the equivalence.
So equivalents are the same for potassium and vanadium?
Yes, because whenever you talk about equivalents, they react in very specific proportions, and they're always equal. That's how it works. So your MM here, I'm just kind of abbreviating there, that's the molar mass for vanadium, so that's going to be 50.9415. And then you're solving for this absolute value of the charge here. Okay? So this is the key part you need to remember for your setup, or once you get to this last equivalent part here. Everyone getting 5? Solving this? So you're going to do, excuse me, you'll do mass. So equivalence, so this is in equivalence per mole. Making sure I keep track of all my units here. So we want to solve for our charge on this one. So we're gonna cross multiply on this. And so you'll have 0.0511 divided into both sides. So then it'll be the absolute value of your charge will be equal to 9415. What does someone get for that? That's going to cancel.
Yeah, I got like a really big number, like 996. That's like, this is the step I've been getting up to. And I've just been like confused as to how it like comes out to be the charge.
Well, your charge is actually just your equivalents per mole. So this is what we're wanting to solve for.
What about the 0.521 grams?
Oh, thank you. Thank you. I was like, we need a mass for vanadium that's reacted. Okay. So we're going to use this 0.521 grams of our vanadium here, we're told, that got reacted and got removed. And we're going to use it to eliminate this grams in our molar mass here. Okay, so that's going to be 50.9415 mole vanadium. Okay, and that's going to give us our moles here. Somebody tell me what they're getting for the moles on this.
Got 0.01. 02.
Okay, I'm sorry, that's the number you're going to plug in right here. I skipped a step. Don't you do that. 0.0102 moles. So that's still put it in the wrong place. So you're going to be dividing this by 0.0102.
Okay, that's coming out to 5.
And the rule we normally use on this equivalence is the same rule that we used for empirical formula, but we really didn't get a whole lot into that. But for final purposes, it has to be within 0.05. As long as it's within 0.05, we can say 5. If not, we need to do a little bit more work, but you all won't have anything like that. That's for stuff that are like F groups that are really crazy. But now then, once we have this, and once we know that the charge on vanadium is +5, the second part for this question we asked was the balanced chemical equation. So if vanadium is +5 and nitrate's a -1, we're going to have 5 nitrates for every single vanadium we have there. And we're told we're just reacting with potassium. There was no other compound with that potassium. So what kind of reaction from this last test we did, what kind of reaction is this? Single displacement, right? This potassium metal is more active than that vanadium. It's going to kick it out. So it's reacting with that. You're going to get potassium nitrate +1 -1, and just vanadium metal kind of filling in your states of matter here. Now we need to balance this. 5 here, we need a 5 here, and a 5 there. Is that one a little bit better now?
Yeah, let me see. Thanks a lot.
What else? Kind of skipped ahead to one on equivalence because you just need to know it for the quizzes. So if there's anyone else doing your 50 quizzes, this is one off of equivalence. I think you all have two kind of like that on there, but they're worded a little bit differently. I think they even he even gives you one that's like an unknown, and he asks you for the molar mass of the unknown or something.
The charge of it, yeah.
Gives you the charge and everything else, and then he asks you to solve for the molar mass, that top portion right there. What else?
Can we do number 10?
Number 10, sure.
After that, can we do number 8?
Mm-hmm. Okay, so number 10, we're told that we have a 20-liter vessel, and it has a mixture of methane and carbon dioxide, so we're kind of thinking of moles for that. We've got a temperature here, the temp that it's at, and we've got a pressure here. And this little X, it's like the side. Be careful with that, it's mole fraction. So you can see it two ways. It kind of looks like, almost like a Nazi symbol, but not. So it's like that for mole fraction, or it's little m, and then a really fancy cursive F. So mole fraction is either one of these. You'll see them as both. So we're told the mole fraction of methane in there is 0.35, and we're asked to find the mass of each gas present. So what type of equation will we use? So we're using ideal, because we don't have changes in, like we don't have one volume and a second volume, we have ones for each. So we're going to be using our ideal. We have a pressure, a volume, and we're really looking for a moles, right? We're really looking for a moles that I can use this mole fraction and get it to a mass. So we're going to be solving for a moles, and we have everything else. So let's do the methane first. So the pressure that all this gas is under is in 5525 torr. Will someone convert that to ATM? So 5525 torr divided by 760. So 4 sig figs in your torr, so you can keep 4 sig figs in your ATM. So 20.5 liters is your volume. So it's already in the right units. We're solving for our moles. We'll always know your gas constant. And your temperature needs to be converted, so 273, was that 310?
305.
306?
Yeah.
So then you can start canceling stuff. So immediately your Kelvin's going to cancel there. And then we want to start doing some solving. So we're going to do 7.270 times 20.5. Okay, so what is somebody getting for N here? So 3 sig figs, so 5.93 moles for our N. Okay. So what's actually interesting for this is the moles of all the gas there. Okay. So this isn't automatically the moles of methane gas. And that's why we needed this second mole fraction part. The second mole fraction told us how distributed it is. Really how much of that is methane and how much of that's CO2. Okay, so your setup for mole fraction is, your mole fraction is the moles of whatever guy you're interested in, so let's do CH4 first, over the total moles. Okay? So you had to have this piece of information because this is the mole fraction for methane. So it's your mole fraction here. So your mole fraction is 0.35. What we really want to solve for is just the moles of methane, right? Because we can do a molar mass and solve that out. So we're solving for the moles of methane. And we know the total moles. That's what we just got done solving for. Okay, so now you're just going to solve for the moles of your methane. Mole fraction has no units because the units are moles and moles, so they cancel. No units there. What's somebody coming up with moles for methane?
2.08.
What's after that 8?
It's 2.076.
Okay. So now you solve for one of them. Another way to do this is have you solve for the mole fraction of the other one, but it really doesn't matter for this problem because if you know the total and you know how much the methane is, you could subtract the total by this and get what the contribution of the other is. So what's that? So 5.93 minus 208, was that 3.85?
Yep.
So 3.85 for our carbon dioxide. And now all we need to do with both of these is just get them into grams. So we're just going to take the molar mass for those, and we'll get those into how much grams of gas is there. So you're going to start out with your methane again. Molar mass for methane should be about 16. 12.011 plus 4 hydrogens. Will somebody give me like an exact, closest to an exact number?
16.04.
Grams per mole. You can go a little bit further with that molar mass. Go as far as you can. Sorry. Yeah, this number should be flipped. And also that one is red marker. Let me redo that. This red marker sucks. So that would get you the grams.
I actually think we were supposed to use Dalton's law. Maybe. In this whole section, it's